In this lecture, we will be studying an advanced version of the limit comparison test for convergence of infinite series. So let's recall the fundamental question when we're looking at convergence of series. We have a sum, n going from 1 to infinity, of a sub n, with all the terms being non-negative, and we want to know, does this series converge? Is this sum finite? And every convergence test attempts to answer the following question. Do these terms, the a sub n, approach 0 fast enough as n goes to infinity for the sum to be finite? And we will see clearly that this version of the limit comparison test directly addresses that. So this version of the limit comparison test says we have two series of positive terms, a sum of a sub n's and a sum of b sub n's. All are non-negative, and for n greater than or equal to 1. And suppose that the limit as n goes to infinity of a sub n over b sub n is 0. And that the sum of the b sub n's converges. Then the sum of the a sub n also converges. This is different than the regular version of the limit comparison test. In the regular version, we had this limit being a positive constant. And here we're saying if this limit of the ratio of the terms is 0 and the sum of the terms in the denominator converges, then the sum of these terms in the numerator also converges. And we can really interpret this naturally when we think about this fundamental question. For a series to converge, the terms of the series have to approach 0 at a fast enough speed, a fast enough rate. And what this tells us is, if we know that the sum of the b sub n's converge, that means the b sub n's are in fact racing to 0 fast enough for the sum of the b sub n's to converge. Then if you think about this limit as a race, so as n goes to infinity, this b sub n, this is going to 0. It's also going to 0 fast enough for the sum to converge, but it is in fact going to 0. For this limit overall to be 0, a sub n has to be going to 0 even faster than the b sub n. In fact, you can think of it as an entire order of magnitude faster. So the b sub n's are going to 0 fast enough for the sum of the b sub n's to converge. If the a sub n's are going to 0 even faster, so that this limit results in 0, then the sum of the a sub n's also converge. And so if we think about this graphically, the b sub n's each of these, or maybe a better way to say it, is as we go down the line, as a sequence, these are approaching 0 fast enough so that this sum converges. But these terms are going to 0 even faster. And again, that is captured by the idea of the limit as n goes to infinity of a sub n over b sub n being equal to 0. Again, the b sub n's are going to 0, so your denominator is going to 0. So if this whole expression goes to 0, a sub n has to go to 0 a whole lot faster than the b sub n does. So, how might we use this? Here's an example where we could use this version of the limit comparison test, and we can do that by noting here the sum n going from 1 to infinity of 2 to the n over n squared times 3 to the n. We could rewrite this as the sum n goes from 1 to infinity of 2/3 to the n times 1 over n squared. And when we look at this, we could think, well, if that 1 over n squared was not there, what would this be? This would be a geometric series with r smaller than 1, so it would be convergent. If we multiply by 1 over n squared, the terms are going to 0 even faster than we need to have the thing converge, because this would converge without the 1 over n squared. Since this would be a convergent geometric series, because it's convergent, we know these terms are going to 0 at a fast enough rate for the sum to be finite. And here, that makes them go to 0 even faster. So why don't we try? So based on that, we have a sense this thing should converge. The terms are going to be smaller than the terms in the corresponding geometric series we just talked about. So why don't we try comparing this with the sum n goes from 1 to infinity of 2/3 to the n, again, which is our convergent geometric series. So put in the jargon of the theorem, we are saying our b sub n is 2/3 to the n. And we can now put this together and use the limit comparison test. So let's look at the limit as n goes to infinity of a sub n over b sub n, or the limit as n goes to infinity of our expression here, 2/3 to the n times 1 over n squared, divided by our b sub n, which is 2/3 to the n. And we see right away the 2/3 to the n terms cancel, and we get the limit as n goes to infinity of 1 over n squared, which is 0. And this is perfectly set up to now use our special version of the limit comparison test. So we have our convergent geometric series. Again, these are our b sub n. We've established that the ratio of a sub n over b sub n as n goes to infinity is 0. That means by applying if we go back to it, our limit comparison test, we have the limit of that ratio being 0, and we know the sum of the terms in the denominator. We know that sum converges. Therefore, the sum of these numerator terms also must converge. For us, our an is this 2 to the n over n squared times 3 to the n. So our original series also converges by limit comparison.